Up until this point, we've mostly been considering a single group at a time, together with its subgroups and its factor groups. But now we're going to start looking at a topic that allows us to, in theory, connect two different groups, even if they are not related in one of those ways. And we're going to do that by looking at functions between them. Now, if I just take two sets, I can construct all sorts of functions between them. And if those sets have a group structure, most of those functions will have nothing to do with that group structure. However, some of them will behave nicely with respect to the multiplication or the addition that's happening on the level of the groups, and those functions we're going to be mostly concerned with. Those are known as group homomorphisms. The definition is as follows. Definition 69 says, let G and G prime be groups. A homomorphism from G to G is G to G prime, rather, is a function phi from G to G prime such that, and there's one condition that has to hold for this function phi to be a homomorphism. However, the one condition we have is a strong and powerful one. The condition we need is that for all G and H in G, we have that phi of GH is equal to phi of G times phi of H. Now, it's important to recognize what's going on here and in what settings the various operations are taking place. The GH on the left-hand side here is the product of two things inside G. So this is a product in G. And so we'll have two elements, G and H, and their product. And those all live inside G. On the other hand, we have the product of phi of G and phi of H. And because the codomain of phi is G prime, that means that this product is a product in G prime. What it means then for a function phi to be a homomorphism is that it connects up and relates the operations on G and G prime, even though they may be different operations, and in fact one of these operations might be written additively and the other one multiplicatively. There are lots of different things that we could do here. But what it's saying is that if I take two objects and I'm going to operate on them, and I'm going to apply the function phi to them, it doesn't matter what order I do them in. If I multiply them and then apply phi, I get exactly the same result as if I apply phi to both of them and then multiply them. A homomorphism from G to G prime is a function which respects the group structure on both the domain and the codomain. Now, for a homomorphism, we have certain names that we give to various sets that we work with often. So, if H is any subset of G, then phi of H is defined to be just the set of all images of elements of the set H. So it's the set of all phi of H's where H belongs to H. Notice that this is a subset of G prime. This is called the image of H, or the image of H under phi. We will often be dealing with more than one homomorphism, so we may specify which image we're talking about. And going the other direction, if H is a subset of G prime, then phi inverse of h is equal to, now phi might not be invertible, and so when phi is not invertible, we can treat this as a new piece of notation. Now, when it is the case that phi is invertible and has an inverse, then the set that we would define using the inverse function and the set that we're about to define wind up being the same thing, so there isn't any confusion in that case. Phi inverse of h is the set of all elements little g of g such that phi of g lies in h. So it's the set of all things in G that get mapped to the set H. And this is called the preimage of the set H. So we can look at the image of a subset of G, and we can look at the preimage of a subset of G prime. Now, if E prime is the identity of G, then phi inverse of the singleton set containing E is known as the kernel of phi, and it's denoted that way. And of course, it's a subset of G, and this is the kernel, Kernel, of phi. It turns out that the kernel of a homomorphism is an extremely important set. It's the set of all elements of G that get mapped to the identity in the target group G prime. And then finally, we can talk about the image of phi is simply im phi, which is just phi of G. It's really it's the same type of notation that we're using up in the first point, where we looked at the image of a subset, and the image of phi is just the set of all elements of G prime that come from elements of G. So we've got these different ways that we can describe the sets connected to a homomorphism. Let's look at some examples. So let's let phi be from Z to Z. Of course, the groups G and G prime can be the same. You can look at a homomorphism from a group to itself, and we do very often. And so let's let it be given by phi of x equals 3x. Let's check that phi is a homomorphism. So to check that phi is a homomorphism, we need to show that phi of x plus y is equal to phi of x plus phi of y for all x, y in Z. Many times, this can be accomplished simply by evaluating either side of this equation and noting that we get the same thing out of it. So, for example, if we look at phi of x plus y, we know that the function phi of x sends any, or the function phi sends any element to 3 times that element. So that means phi of x plus y is 3 times x plus y. And we can, of course, distribute that to just be 3x plus 3y. But now notice that once we've done that, 3x is exactly phi of x, and 3y is exactly phi of y. And so we see that this function, the multiplies by 3 function, is in fact a group homomorphism from Z to Z, because it doesn't matter whether you add the two elements before taking the function or afterwards. Or I had that backwards. But the point is that the order that you apply the function and the operation doesn't matter. So let's look at some of the other types of sets that we had before. So let's let H be the set 6Z, which is a subgroup of Z. So we also have another way of describing this. H is equal to 6x for all x in Z. So we have that the image of H under phi is the set of all phi of H, where H belongs to, a little h belongs to H. But we can work out more of what this is. An element little h belongs to capital H if and only if it looks like one of the things in H. It's a 6x. So we can say that taking phi of H for all h and x is the same, h and h, big H, is the same as saying take phi of 6x for all x in Z, because that's what the elements of big H look like. And now we know what phi of 6x is, because phi multiplies anything by 3. So phi of 6x is 18x for all x in Z, which we can write as 18Z. So the image of the set 6Z is 18Z under this homomorphism. So that's the image of H. Let's look at the preimage of H. So the preimage of H will be the set of all x in Z such that phi of x lies in H. So working out what this means, this is going to be the set of all x in Z such that 3x is in 6Z. So it's going to be the set of all x's such that 3 times x is a multiple of 6. Well, because 6 is 3 times 2, 3 times x is only going to, or 3 times x is only going to lie in 6z if x is even. So this is going to be the set of all x in Z such that x is in 2Z. And so that'll give us the set 2Z, of course. So that tells us that the preimage of H, the set of all things in Z that get mapped into H by this function phi, are the even numbers 2Z. We also have that the kernel of phi is the set of all integers that get mapped to 0. So it's the set of all x in Z such that phi of x is 0, since 0 is the identity of the codomain Z. So that's the set of all x in Z such that 3x is equal to 0. But of course, there's only one number that has the property that 3 times that number is 0, and that's 0. So the kernel of phi is just the set containing 0, and the image of phi is just the set of all elements that show up as the image of something in phi, so that's going to be 3z. There's an example of a homomorphism. It's also helpful to see examples of functions that are not homomorphisms. So let's see an example. Let phi from z to z be given by phi of x equals x plus 1. Now, if you are suspicious that a particular function might not be a homomorphism, one thing you can do is just try grabbing 2 random elements of your domain and try checking the condition for being a homomorphism on those. Because if you can show that phi of x plus y is not equal to phi of x plus phi of y for even one example, x and y, then that means phi is not a homomorphism. In this way, being a homomorphism is a bit of a fragile condition in that if even one pair of x and y make this equation not an equation, then phi is not a homomorphism. So let's try doing that. Let's just try picking two random numbers, evaluating phi of x plus y and then phi of x and phi of y, and seeing whether we get an inequality here. So let's consider x equals 3, y equals 8. And we could try looking at phi of 3 plus 8, and we're going to compare that to phi of 3 plus phi of 8. Now, phi of 3 plus 8 is phi of 11. And we know that phi of any number gives us that number plus 1. So phi of 11 is 11 plus 1, which is 12. Now, to evaluate phi of 3 plus phi of 8, we evaluate each one of those separately. Phi of 3 is going to be 3 plus 1. Phi of 8 is going to be 8 plus 1. So we wind up with 3 plus 1 plus 8 plus 1, which is 13. So in particular, that means that phi of 3 plus 8 does not equal phi of 3 plus phi of 8. So that means that phi is not a homomorphism. So this is how we can tell that a function is not a homomorphism. If you ever want to prove that a function is not a homomorphism, you just give a single example of a pair of elements from your domain which make the homomorphism defining equation fail. Let's look at a couple more examples. One that we can use calculus to look at is the following. Let's let G be the set of polynomials with complex coefficients. And let's let delta from G to G take a polynomial to its derivative. So we can look at some things about this function. First of all, we have that delta of f plus g is equal to f plus g prime, which we know from calculus is equal to f prime plus g prime, because the derivative of a sum is the sum of the derivatives, which gives us delta of f plus delta of g, which means that delta is a homomorphism. All right, let's look at the image of delta. The image of delta is going to be the set of all polynomials in G such that f is the derivative of something. So it's the set of all. Let me rewrite this slightly in a slightly better way. So the image of delta is simply the set of all delta of f's, where f belongs to G. And so this means that an element G is in the image of delta if and only if there exists an f in G such that delta of f equals G. or in other words, an antiderivative of g. Since every polynomial has an antiderivative, we know this from calculus, since every polynomial has an antiderivative, this means that the image of delta is in fact all of g. So delta is in fact a surjective function, a surjective homomorphism. And now finally, if we want to know the kernel of delta, this is going to be the set of all elements of our group G such that delta of f is equal to 0. Now, we know that the derivative of a function is equal to 0 if and only if the function is a constant function. So this is the set of all f in G such that f is a constant function. Or a constant polynomial, I really should say. So this is a good example of a function that has a non-trivial kernel. This one actually does send more things to 0 than just the identity itself. All right, let's look at one where the operation is multiplication. Let's let G be the general linear group of matrices with real coefficients. Remember that this is the set of all matrices A, B, C, D, where A, B, C, and D are real numbers and their determinant is not equal to 0. And now I want to look at the function det for determinant. And det is going to go from the group G to the real numbers except 0 under multiplication. So remember, this is the set of real numbers except 0 under multiplication. Where this det of m is the determinant of m. Now we know from linear algebra that the determinant of a product of matrices is equal to the determinant of, or the products of the determinants of each one. And that means that the function determinant is a group homomorphism. And we can look at the image of determinant. And this is going to be the set of all real numbers that show up as the determinant of some matrix. Now we're going to claim that the image of det, the function det, is in fact all non-zero real numbers. We'll do that in the following way. We'll say that since for any little r in r cross, any non-zero real number, we have that the determinant of the matrix R001 is equal to R. So that shows that the determinant function is, again, a surjective function because its image is the whole codomain. Let's look at the kernel. The kernel of the determinant function will be the set of all matrices in G such that the determinant of M is equal to 1, because 1 is the identity element of the codomain. And we actually had a name for this. We called this the special linear group of matrices, of 2 by 2 matrices over the real numbers. So, in fact, that group that we looked at before, we can recognize as the kernel of a group homomorphism. It turns out, we'll see in a second, that we could have used this information to prove that the special linear group is a normal subgroup of the general linear group, which we did directly before. All right, and so let's consider what happens when we want to do a homomorphism of factor groups. Here's where we have to be a little bit careful. Not only with factor groups, but other situations where a single element can have multiple representatives. And this is something that we've addressed before, so I'm going to mention it again here briefly. So when the elements of G have different representatives, we must check that a map, or that a homomorphism, a potential homomorphism, phi from G to G prime, is well defined. That is, we need to check that if x equals y, where x and y are two different ways of writing down the same element of G, then we need to make sure that phi of x is equal to phi of y. Let's see an example where this fails, so that we can know what to be on the lookout for. So let's let phi be something that goes from z mod 3z to z mod 4z, be defined, in quotation marks, by phi of, now in order to keep track of the fact that I've got two different factor groups going on here, I'm not just going to use the bar notation from before. I'm going to go ahead and use the coset notation. So I want to define it by saying that phi of x plus 3z is equal to x plus 4z. Now, if I'm not careful, I might go on merrily from here and conclude that this is a group homomorphism and start looking at things that we can measure about it, like its kernel and so forth. But whenever we're dealing with a domain that has elements that have different representatives, we have to be careful. And we have to make sure that the function is well defined. So in this case, it turns out that the function is not well defined. So we can see that in an example. So notice that 1 plus 3z is equal to 4 plus 3z. Those are 1 and 4, just two different representatives from the coset 3z. Two different representatives of the same coset of 3z. But we have that phi of 1 plus 3z, by the definition, is 1 plus 4z, and phi of 4 plus 3z is equal to 4 plus 4z, which is 0 plus 4z. In particular, this means that phi of 1 plus 3z is not equal to phi of 4 plus 3z, but the two elements that we're starting with down here are equal to one another. So that means that phi is not well defined. So an interesting exercise is to look at this map, but for different values of the cosets down below. So look at Z mod 6Z and Z mod 4Z, or Z mod 12Z and Z mod 4Z, or change up the group on the right and see what pairs of cosets here will give you a well-defined function and which won't. Some of them will and some of them will not. All right, so let's see what we can tell about elements of the group G based on a homomorphism coming from G. Theorem 70 has some of the essential components. So let's let phi from G to G prime be a group homomorphism. And let's let A and B be elements of G. We've got a few different points here. So if E and E prime are the identities of G and G prime, then phi of E equals E prime. So first of all, notice that now that I'm dealing with two groups, I'm making very explicit what the identities to them are. So far, we have been using E as our default notation for the identity of our group, but that's only safe when there's only one group involved. If there are two groups involved, then there could be there will be one identity for the first group and one identity for the second group, and we don't want to use the same symbol for them because they aren't the same element, and we don't want there to be any confusion about which one we are using. So when you are dealing with more than one group at a time and you want to make reference to their identities, you must specify what your symbols mean. So as I've done here. If E and E prime are the identities of G and G prime, I really should say respectively. So E is the identity of G and E prime is the identity of G prime. Once we've done that, then we can make statements like phi of E equals E prime and have it make sense. Now notice what this is saying. It's saying that a group homomorphism always sends the identity of the first group to the identity of the second. The identity of the domain maps to the identity of the codomain. This is something that is just always true. Number two, if I take phi of a power, then that's the same as taking the phi first and then raising to the power. And this is for all powers n, including negative ones. Number three, if the order of A is finite, then the order of phi of A, we can't say that the order of phi of A necessarily equals the order of A, but we can say that it divides the order of A. There's a relationship there. And number four, and this is potentially the most important one that we've got in this whole theorem. If phi of A is equal to phi of B, not if, but phi of A equals phi of B if and only if A inverse B is in the kernel of phi. In particular, this means that phi is injective if and only if the kernel of phi is equal to just the identity. Now notice that part 1 proves that the element E is always in the kernel, because E always gets mapped to E prime. The identity of G always gets mapped to the identity of G prime. If it's the only thing that gets mapped to the identity of G prime, part 4 is telling us that means that your function is injective. It's going to turn out that we're going to care a lot about whether group homomorphisms are injective, and it's going to be much more efficient to prove that by proving that their kernel is trivial, that is the smallest it could possibly be, rather than directly in almost all cases. All right, let's see the proof of this, at least a sketch. So for part 1, we want to show that phi of E is the identity element of G prime. The advantage here is that we know that there's only one identity of G prime, and it's the only element that has the property that when you multiply it by something else in G prime, you get that same thing back. So let's let so notice that we have the following. We have that phi of E times E is equal to phi of E times phi of E, since phi is a homomorphism. But we also have, of course, that phi of E times E is, of course, just phi of E, because E times E is E, because E is the identity of G. So we have that phi of E is equal to phi of E times phi of E. At this point, we don't know what phi of E is, but if we multiply both sides by phi of E inverse, we know that any element in G prime has an inverse. And if we do that, then we'll get that on the left, we'll get phi of E inverse times phi of E. Those cancel out and just give us E prime. And on the right, the phi of E inverse will cancel with one of the phi of E's, which will give us phi of E. And so we get exactly what we want there. Part 2 we can handle in 2 steps. The first step is to handle the non-negative ends, and then we'll handle the negative ends. So for part 2, we want to show that phi of A to the n is equal to phi of A to the n. We have that if n equals 0, then this is simply saying that phi of A to the 0 is equal to, we have that, phi of A to the 0 is just phi of E. We know that. I should have written that the other way. We have that phi of A to the 0 is equal to phi of E. We know already from part 1 that that's equal to E prime, the identity of G prime, and so that's definitely the phi of E to the, or phi of A, rather, to the 0th. All right, so that handles the n equals 0 case. If n is greater than 0, then we can, technically we would use induction on this, but the intuition behind it is the following. If we have phi of A to the n, that's phi of A times A times A times A up to A, and this is n times. Now, because phi is a homomorphism, we can take all of these multiplications and split them up, right? This is phi of A times phi of A all the way out to phi of A, again, n times. And that equation is because phi is a homomorphism. And that, by definition, is phi of A to the nth power. So that's if n is greater than 0. Now, let's look at if n is equal to -1. We'll handle that case separately. So we want to show that phi of A inverse is equal to phi of A inverse. Now, the way to show that one element is the inverse of another element is to multiply them together and show that you get the identity. We have that phi of A inverse times phi of A is equal to phi of A inverse A. That's because phi is a homomorphism. That's phi of the identity. And by part 1, phi of the identity E is E prime. So that means that these two elements that we started with are inverses of each other. And in particular, this means that phi of A inverse is the inverse of phi of A. And so finally, if n is less than -1, then we can say that phi of a to the n is equal to phi of a to the -1 raised to the -n. Now, of course, -n is positive. In fact, it's greater than 1. And so we can use the previous result on positive numbers to say that this is phi of A inverse to the -n. The previous result says that phi of A inverse is phi of A inverse. And then we can use properties of exponents in G prime to get that we have phi of A to the nth power. So part 2 says that we can move powers in and out of homomorphisms. All right, part 3 follows pretty much immediately from part 2. So part 3, we want to show that the order of phi of A divides the order of A. So we have that phi of A raised to the order of A by part 2 is phi of A raised to the order of A. By definition, A raised to the order of A is the identity, and by part 1, phi of the identity is the identity. So now we have that the element phi of A, when raised to this power, the order of A, gives us the identity. So by a previous theorem, which I don't have at hand, by a previous theorem, we know that if an element raised to a power gives us the identity, that tells us that the order of the element has to divide that power. All right. So now, finally, we have part 4, and so that means that we want to show that phi of A equals phi of B if and only if A inverse B is in the kernel of phi. So let's go ahead and do that. In this case, we're going to go ahead and do the if and only if all in one step, where rather than going in one direction and the other, what we're going to be able to do is connect up a sequence of statements, starting with the first one, phi of A equals phi of B, and ending with the last one, but all the statements are going to be connected with if and only ifs rather than an implication going in one direction. So to show this, we'll say that phi of A equals phi of B. This happens if and only if the identity, E prime, is equal to phi of A inverse times phi of B. So this is just multiplying both sides by phi of A inverse. And that happens if and only if E prime is equal to phi of A inverse times phi of B. This is by part 2. That happens if and only if E prime is equal to phi of A inverse B, and that's because phi is a homomorphism. But this happens if and only if A inverse B is in the kernel of phi. Remember, the kernel of phi is the set of all elements that get mapped to the identity. It's the set of all elements x such that phi of x is E prime. So in this case, we managed to prove an if and only if statement by stringing together if and only if statements from beginning to end. This is not always the case. You typically only want to do it with reasonably simple arguments like this, where we just have a few very simple steps, because many of the arguments we make actually aren't perfectly reversible like this. They aren't perfectly if and only if statements, but in this case, it worked out. So now let's handle the in particular part now we want to show that phi is injective if and only if the kernel of phi is only the identity E. Now let's suppose that the kernel of phi is the identity. And let's let A and B be in G such that phi of A equals phi of B. Well, then that means by the first part of part 4, then that means that A inverse B has to be in the kernel of phi. Now we've supposed that the kernel of phi only contains one element E. So that means that A inverse B has to be the identity itself. And if A inverse B is E, then if we multiply by A on the left on both sides, we get that B is equal to A. So that means that phi is injective. So we suppose that the kernel of phi was just the identity. We assumed that we had two elements such that phi of A equals phi of B. We concluded from that that B has to equal A, and therefore phi has to be injective in this case. Now, if phi is injective, or let's say suppose phi is injective. Suppose phi is injective, and let's let x be in the kernel of phi. Well, then that means that phi of x is the identity E prime, but we also know that that's phi of E. Since phi is injective, that means that x and E have to be the same thing. So this tells us that the only element of the kernel is the identity, and therefore the kernel is just the set containing the identity. Okay, so we've got these various properties of homomorphisms. As I said, the one that we are going to use most often is probably the last part of part 4 here. Let's see an example for how that happens. So let's let phi be a map from the group C to the group C. Now remember, this is under addition. Be given by phi of A plus bi is A minus bi. It's the conjugate function. Now it's an exercise to show that phi is a homomorphism. But let's try to show that phi is injective. Now, going about things the normal way for proving that just a general function is injective, we would say let's take a plus bi and maybe a prime plus b prime I. Take two elements, assume that they map to the same thing, and then make an argument about why they actually had to be equal to begin with. Because phi is a homomorphism, we can be more efficient about this. We can prove that phi is injective by computing the kernel. So let's find the kernel of phi. So the way that we will typically do this is the following. Let's let some element be in the kernel of phi. Therefore, that means that 0 is equal to phi of a plus bi, because 0 is the identity of C, and if a plus bi is in the kernel of phi, that means that phi of a plus bi is 0. But we also know, by the definition, that a plus bi, phi of a plus bi is a minus bi. Now, in order for a complex number like a minus bi to be equal to 0, both the real and imaginary parts have to be 0. So this means that a equals 0 and b equals 0. So a plus bi is in fact equal to 0. Now we just started off by assuming that a plus bi was just any element of the kernel. And we showed that if we take any element of that kernel, then that element has to be 0. So in other words, that shows that the kernel of phi has to be just the number 0. And hence that means that phi is injective. Well, let's look at another one. One that's not quite as obvious. The previous one was fairly obvious. This one not so much. Let's let phi from z to c cross. So this is now the non-zero complex numbers under multiplication be given by phi of n is e to the n I, which is cosine n plus I sine n. If you haven't seen this before, this is a typical way of, or a common way of writing down complex numbers in exponential form. And e to the ni is just defined to be cosine of n plus I times sine n, that complex number. Now, phi of n is equal to 1, which is the identity of the group C cross, if and only if n is a multiple of 2 pi. Those are the only numbers that you can plug into cosine to get 1 out of them. So phi of n is equal to 1 if and only if n is a multiple of 2 pi. But since pi is irrational, the only integer multiple of it is 0. So that means that the kernel of phi is in fact just the number 0 again. So we've got a whole bunch of complex numbers that we get out of this, but what this argument shows is that this phi is injective. That is, you'll never get the same complex number out of this function phi by applying or when plugging in 2 different integers. All right, so this is how the elements phi or the homomorphisms phi interact with elements. Let's look at how they interact with subgroups of G. Theorem 71 has quite a few parts to it. So let phi from G to G prime be a homomorphism. H a subgroup of G, and H prime a subgroup of G prime. All right, we've got 7 statements here. First of all, the image of a subgroup is a subgroup. So phi of H is a subgroup of G prime. Image of a subgroup is a subgroup. If H is cyclic, or respectively abelian, so is phi of H. So the image of H is going to have a lot of the same properties that H does. So if H is a cyclic subgroup or is an abelian subgroup, then so will phi of H be. I should mention that we often apply this theorem when H or H prime are just the whole groups that they belong to. Number 3, if H is a normal subgroup of G, then unfortunately we can't then say that phi of H is going to be a normal subgroup of G prime. G prime could be much, 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 much bigger than G, and since being a normal subgroup relies on interacting with all of the other elements in the group, weird things can happen in G prime that didn't happen back in G. So we can't necessarily say that phi of H is a subgroup of G prime, but we can say that it's can't say it's a normal subgroup of G prime, but we can say it's a normal subgroup of phi of G. Number 4, we have that the preimage of H is a subgroup of G, so sort of the inverse to part 1. Part 5, if H prime is a normal subgroup of G prime, then phi inverse of H prime is a normal subgroup of G. This one we actually can write down as being a normal subgroup of the whole group G itself. And that's basically because phi isn't required to be surjective. There could be things in G prime that phi doesn't map onto. But phi certainly is required to take every element of G somewhere. So if H prime is a normal subgroup of G prime contains all of the things that phi maps G to. And so when we pull the subgroup H prime back to G, we maintain normality. So the preimage of a normal subgroup is a normal subgroup. In particular, this is a very important one, the kernel of phi is a normal subgroup of G. This is going to be one of the ways that we can very easily know whether a subgroup is normal or not, is if we can recognize it as the kernel of some homomorphism. For any H prime in phi of H and H in H such that phi of H equals H prime, we have that phi inverse of the singleton H prime is equal to H times kernel of phi. In particular, we have that if the order of the kernel of phi is n, if it's finite and is equal to n, then phi inverse of H prime, the order of phi inverse of H prime, is n. Now, this is a a sort of long-winded way of saying that every element has the same number of preimages. So for the function phi from G to G prime, if you've got some element in G prime that has, say, 7 preimages, then every element that's in the image will have 7 preimages. There might be some things that have no preimages at all that aren't hit, but if something is in the image of phi, then we can measure the number of preimages it has by looking at the number of preimages of anything else. All right, and then number 7 says that if the order of H is finite, then the order of phi of H divides the order of H. This one takes a little bit of work. This number 7 here requires us to have number 6 above because we're looking at orders of groups rather than orders of elements. We've got to work a little bit harder at it. All right, so let's run through a couple of these. So let's look at part 1, proof. Part 1, so this was saying that the image of H is a subgroup of G prime, and really this all comes down to the fact that the things in phi of H behave by the homomorphism restriction like things in H itself. So, for instance, we have that E prime is equal to phi of E, which is in phi of H because, of course, the subgroup H has to contain the identity element E. So that means that phi of H is non-empty. And then if A and B belong to phi of H, the thing that we do here is what we do a lot of times, is we're going to let X and Y belong to H such that phi of X equals A and phi of Y equals B. Many times we're going to want to prove something about phi of H, which means that the one thing that we know about the elements of phi of H is that they are the images of some element of H under the homomorphism phi. So we work with that. So given this, we can use the one-step subgroup test to say that, so this means that A times B inverse is equal to phi of X times phi of Y inverse, but we know that phi of X times phi of Y inverse is phi of XY inverse, and that's because phi is a homomorphism, but we also know that H is a subgroup of G, and because X and Y belong to H, X times Y inverse has to belong to H, and therefore phi of XY inverse is phi of something in H. So therefore, phi of H is a subgroup of G prime by the one-step subgroup test. All right, number 2, we wanted to say if H is cyclic, so is phi of H. I'll do the cyclic portion here. The abelian one is similar, and it's an exercise. So that's what we want to prove. So let's suppose that H is equal to the cyclic subgroup generated by A. So let's suppose H is cyclic. And so now we want to show that phi of H is cyclic. We claim that phi of H is the subgroup generated by phi of A. That's the natural thing to choose. In order to show that phi of H is a cyclic subgroup, we have to show it's generated by some element. The only element that we have to work with at this point is A, but A lives back in G, and so to get something in G prime, we apply phi to it to bring it up to G prime. So to show that phi of H is the cyclic subgroup generated by A prime, we need to show that anything in H can be written as some power of phi of A. So we could let B be in phi of H. That means that there exists some, not A, there exists some C in H such that phi of C equals B. But since C is in H, which is the cyclic subgroup generated by A, there exists some integer n such that C is equal to A to the n. So this means that B is equal to phi of C, which is equal to phi of A to the n, which we know by the previous theorem is phi of A to the n. So we showed that given any element of phi of H, we could write it as a power of phi of A, which proves that phi of H is in fact the cyclic subgroup generated by phi of A. So in fact, we've shown even a little bit more than what this the problem statement or theorem statement said. Not only have we shown that if H is cyclic, so is phi of H, but we've also shown that any generator of H maps to a generator of phi of H. All right, number 3, we wanted to show that if H is a normal subgroup of G, then phi of H is a normal subgroup of phi of G. So for this, we'll say we want to let A be in phi of G, which means that, and we want to show that A times phi of H times A inverse is a subset of phi of H. So let's do that. Now, since A is in phi of G, there exists X in G such that phi of X equals A. So that means that A times phi of H times A inverse is equal to phi of X times phi of H times phi of X inverse. Since phi is a homomorphism, we've got that this is phi of X times phi of H times phi of X inverse. And rather than applying phi and then doing all the operations, we can apply all the operations first and then apply phi. So this is all equal to phi of X times H times X inverse. Now we know that H is a normal subgroup of G and X belongs to G, and therefore this means that this is all a subset of phi of H, which is exactly what we wanted to show. So that shows us that phi of H is a normal subgroup of phi of G. Now let's think about why this argument doesn't show that phi of h is a normal subgroup of G prime. We don't have this necessarily. Let's go through the theorem and see what fails. So what if instead of saying let A be in phi of G, we just said let A be in let just A be in G prime. We still want to show the same thing. And so if A were in G prime, there exists X and G such that phi of X equals A. That's where we would run into problems. So this statement right here wouldn't apply if we were trying to show that phi of H was a normal subgroup of G prime. Note, however, that if phi happens to be surjective, then phi of G is in fact equal to G prime, and so in that case we would get that phi of H is a normal subgroup of G prime, but only in the case that phi is surjective. All right, number 4, we wanted to show that phi inverse of H prime is a subgroup of G. This is going to be very similar to part 1. We have that phi of E is E prime, which belongs to H prime, so that means that E has to belong to phi inverse of H prime. So that means that phi inverse of H prime is not empty. So now let's let X and Y be in phi inverse of H prime. And we're going to try to show that X times Y inverse is also in phi inverse of H prime. Now the way that we show that some element is in the pre-image of a set is to show that phi of that element is in the set that we talk about. So in order to prove that X times Y inverse is in the set phi inverse of H prime, that is the same as showing that phi of XY inverse belongs to H prime, which is how we're actually going to go about proving this. If you want to show that something's in the pre-image of a set, then apply the homomorphism to that element and show that you lie in the set that you were considering before. So we have that phi of XY inverse, by the fact that phi is a homomorphism, is phi of X times phi of Y inverse. Now, we have that phi of X belongs to H prime, and phi of Y belongs to H prime, and we have that H prime is a subgroup of G. That's what that's part of our hypotheses. And therefore, this is all contained in H prime, since H prime is a subgroup of G. Now, this statement, phi of XY inverse is contained in H, immediately becomes that XY inverse is in phi inverse, or the pre-image of H prime. So that means that phi inverse of H prime is a subgroup of G by the one-step subgroup test. All right. Part 5 says that if H prime is a normal subgroup of G prime, then phi inverse of H prime is a normal subgroup of G. And then there's an in particular statement, which we'll handle afterwards. So let's let X be in G. We want to show that X times phi inverse of H prime X inverse belongs to phi inverse of h prime. Now, this is this notation here is getting a little bit complex, but let's walk through things carefully. We're trying to show that some stuff here, and I really should have written subset rather than is an element of. It wasn't correct before. We're trying to show that this element here is in the pre-image of h prime. This is the same as showing that phi of this stuff, x phi inverse h pre-image of h prime x inverse, is a subset of h prime. So let's try to show this. We have that. So this is what we're trying to show. We wouldn't necessarily put this down into a formal proof. We have that phi of x phi inverse h inverse x inverse is equal to, because phi is a homomorphism, phi of x times phi of phi inverse of h prime times phi of x inverse. Now here's where we do have to be a little bit careful, because of course this notation phi inverse right here, or pre-image I should say, I keep saying phi inverse because that's the notation, we're using the same notation as for inverse, but phi might not have an inverse, phi might not be invertible. And so when I've got a phi and a phi inverse here, I can't necessarily cancel them out because phi might simply not be a bijection. So we do want to know how we can simplify something like phi of phi inverse of h. So we can visualize this in the following way, which is how I like to think about it. So we've got g prime and we've got g over here. And then we've got h prime, and we've got a function phi that goes between them. Goes from g to g prime. All right. So now, if I look at the pre-image of h prime, what that's going to be is it's going to be a collection of a whole bunch of points, a whole bunch of elements of G that all get mapped into H prime. That's the definition of what the preimage is. It's, all the points in G that get mapped into H prime. So now if I actually do apply phi to that, then I'm going to be taking each of these green points and mapping it to their target red points over here in G prime. Now what I can see from this is that all of the green points will get mapped to something in H prime. So we can say that if x is in phi inverse of h prime, then phi of x will be in h prime. That's the definition. And so that tells us that phi of phi inverse of h prime is a subset of h prime, but the point is we can't do any better than this. We always have this relationship right here when working with pre-images, but we can't necessarily say we have equality unless we are dealing with honest bijections and hence inverses. So this next step in our computation, we have phi of x times phi of phi inverse of, or pre-image of h prime times phi of x inverse. Our next line should, or next step should look like is a subset of phi of x times h prime times phi of x inverse. Fortunately, that's all we need. We're only trying to prove is a containment here. And in fact, we have that now phi of x is just some element of G prime. That's all we care about. And so we know that H prime is a normal subgroup of G prime, and therefore if I take anything in G prime and multiply on the left by it and on the right by its inverse, then that will be a subset of H prime. So this is since H prime is a normal subgroup of G prime. All right, so we've shown that phi of all this stuff is contained in H prime. So that means that x times phi inverse of H prime times x inverse is contained in phi inverse of H prime because it gets mapped into H prime under phi. But that's exactly the condition that we need to conclude that phi inverse of H prime is a normal subgroup of G. Okay, so now let's get to the next, the last step, which was the had the sort of complicated expression. It said that for any H prime in the image of phi, or the image of H under phi, and H in big H such that phi of little h equals H prime, we have that phi inverse of H prime, that is the preimage of H prime, the set of all the things that get mapped to H prime, is H times the kernel of phi. Basically, if I have any preimage of H prime, then any other preimage of H prime will look like H times something in the kernel. So, in particular, if the order of kernel phi is some number, then the preimage of any element H prime in the image of phi is that same number. So let's prove this. This is just a restatement of what we were trying to prove. We know from the previous theorem that phi of x equals H prime, which is phi of H, if and only if H inverse x is in the kernel of phi, which happens if and only if x is in H times the kernel of phi. If H inverse x is in the kernel of phi, then that means that H inverse x is equal to some k, where k is in the kernel. And therefore, if we multiply on both sides by H, we have that x is equal to HK, which, of course, is in H times the kernel of phi. So that tells us that the preimage of any element is a coset of the kernel, and the coset of the kernel is, of course, represented by any of its elements. So, in particular, for the in particular part, we know that the order of phi inverse of H prime, or the preimage of the set containing H prime, is equal to the size of the coset H times kernel of phi, which is the same as the size of the coset kernel of phi. We've proved before that the size of all cosets of a subgroup are equal. And so that's n. Now, I just realized that we neglected to do the in particular part for part 5, but that's very quick, so let me handle that now. So for part 5, the in particular said that in particular the kernel of phi is a normal subgroup of G, and this is since the set containing just the identity element of G prime is a normal subgroup of G prime. The set containing just the identity element of a group is always a normal subgroup of a group, and by definition the kernel of phi is equal to phi inverse of this normal subgroup of G prime. So that's all that there was to the in particular part of part 5. All right, finally, part 7 says if the order of H is less than infinity, then the order of phi of H divides the order of H. We have that for any H prime in phi of H. We know that the preimage of H prime is H times the kernel of phi, where H is a preimage of H prime, is any preimage of H prime. Thus, this means that if I take the elements of phi of H and look at each of them comes from the same number of preimages beforehand. So every element of phi of H is the image of a number of elements of G that is equal to the order of the kernel of phi. So it's the image of order of kernel phi elements of H, or rather it's the image of this many elements of G. So now fixing this to get exactly what we need, I should have backed up and defined new function phi that only goes from H to phi of H to make this work. So so let me go ahead and do that now. Sorry for having to put that in afterwards. Let's see how this goes. Let's let phi restricted to H from H to phi of H be the restriction, of phi to h. So this is the function phi, which takes an element of h and maps it to one of the elements of phi of h. Now, it turns out that if you restrict a group homomorphism to a subgroup, it is still a group homomorphism. That's an exercise. Pardon me. And so now, thus, we may assume, in fact, that h is equal to g. By restricting down to only consider h, we can reduce to the case where phi, or where h is in fact all of g, and we're just looking at not a subgroup, but a group itself. So, going through here, all this goes exactly the same, except that we actually can write that phi of h, every element of phi of h is the image of this many elements of h, because now h is the whole group. And so thus we have that the order of phi of h is equal to the order of h divided by the order of the kernel, which gives us what we want. That means that phi of h divides the order of phi of h divides the order of h. All right, so that finishes that off. Sorry for that little hiccup at the end. All right, so as before, there's one part of this theorem which we use very often, and that's that the kernel of a group homomorphism is always a normal subgroup. Sometimes using that will give us an easier way of proving that a particular subgroup is normal than others. So, for example, let's let G be the group GL2R, which we've seen before, and let's let H be the subset of G, be the matrices with rational determinant. Now, at this point, we're not claiming that H is a subgroup or a normal subgroup or anything. We're just saying let's take the collection of all the matrices in GL2R which have rational determinant. We're actually going to show that H is a normal subgroup, which is going to prove that it's a subgroup and that it satisfies the normal condition. And we're going to do that by proving that it's the kernel of a particular, or the preimage rather, of a particular normal subgroup. So now we know that the determinant function from G to R cross is a homomorphism. We saw that before. Homomorphism. And then also we have that H is the inverse under this map of the set of non-zero rational numbers. So it's all the matrices with rational determinant. That is, it's all the matrices whose determinant is a rational number. Or, in other words, it's the preimage of the set of rational numbers under the determinant homomorphism. Now, since R cross is abelian, we know that Q cross is a normal subgroup of R cross, because every subgroup of an abelian group is normal. So that means that H is a normal subgroup of G by theorem 71. So we can prove we didn't have to go through the one-step subgroup test. We didn't have to check the normality condition directly. Simply by showing that it is the preimage of a normal subgroup under a group homomorphism, you prove all of those things. All right, so what about a normal subgroup? If I have a normal subgroup, is it always the preimage of a normal subgroup in some other group? Or more specifically, is it always the kernel of some homomorphism? And the answer to that is yes. So Theorem 72 says that let G be a group and H a normal subgroup of G. There exists a homomorphism phi from G to G prime such that H is the kernel of phi. So to prove this, this proof is more satisfying than some of the ones that we have, because we are going to get to construct this homomorphism very, very explicitly. We're going to say let G prime be the factor group G mod H. We know we can do this because we've assumed that H is a normal subgroup of G. Therefore, we can form the factor group G prime. And let's let phi be the function from G to G mod H be given by phi of x is equal to xh, where xh is, of course, the coset of h with representative x. Now we have that phi is a homomorphism basically by definition, but we can see it explicitly. If I take phi of xy, that is by our construction here, that's xyh, but we know by the definition of multiplication on factor groups that that's the same as xh times yh, which is phi of x times phi of y. So proving that phi is a homomorphism is completely direct. There's nothing too clever about that. And then also we have that the kernel of phi is the set of all x's such that xh equals h, but we know that the only elements that do that are the elements of h. So we managed to construct a homomorphism with h as its kernel. So you'll note that this map from G to G mod H is very natural. There are no decisions to be made here, and it always exists in exactly the same way. It's very standard, and it has a name. This is called the projection map. From G to G mod H, and we often denote it pi for P for projection. However, you shouldn't assume that if a map is called pi, it is necessarily a projection like this, but it is a pretty common convention to use. All right, the final note for today, and the proof of this will be an exercise, is that group homomorphisms behave nicely with respect to composition. Theorem 73 states that if phi from G to G prime and psi from G prime to G double prime are homomorphisms, then so is psi phi, which goes from G to G double prime. So stringing homomorphisms together, any number of homomorphisms, will give you another homomorphism, which we will take advantage of pretty often.